Hello fellow Homo sapiens, and welcome. Take a moment to settle in. Whether you're preparing to sleep, unwinding after a long day, or simply letting your mind wander while cooking, showering, or working with headphones on, this space is for you. Here, we explore slow science and quiet storytelling. No hype, no noise, just careful history, humble archaeology, and thoughtful reflection told softly. If this kind of long-form content speaks to you, consider liking and subscribing. It helps others discover a calmer way to learn and grow curious. I'd also love to hear how you use these stories. Do you listen at night before sleep, or during the day while working? And don't worry if you drift off in the middle. I've added timestamps in the description so you can easily return and continue the journey, because every part of the story is worth hearing through. So wherever you are, stay curious, stay calm. Tonight, we begin. Having the sun as your neighbor is hard. Searing hot temperatures, deadly radiation, and the onslaught of meteor collisions don't exactly make it the most welcoming part of the solar system. As you can imagine, these challenges make Mercury a particularly tricky place to get to. For this reason, even though it's much closer to us than Jupiter or Saturn, Mercury remains relatively unexplored. Still, scientists managed to send two different missions out to study Mercury. Mariner 10 flew by in the 1970s, followed by NASA's Messenger in 2015, which was the first probe to ever successfully orbit the planet. And now, as I speak, a third Mercury mission is hurtling through the constellation of Pisces, over 177 million kilometers away from Earth. Bay Colombo, a labor of love between the European Space Agency and the Japanese Aerospace Exploration Agency, is set to arrive on December 5, 2025. It will carry out a comprehensive study of the planet's magnetic field, surface, and internal structure. But as they say, the journey is the destination. And Bay Colombo's journey is a long one. I'm Alex McCohen and you're watching Astram. Join me today as we reveal what Bay Colombo has revealed of Mercury so far, why it's traveling farther than the distance of Pluto to get there, and what we're hoping to learn about the closest planet to the Sun. On October 20th, 2018, Bay Colombo took off from the French Guiana Space Center, beginning its 7-year journey to Mercury. Its trajectory would take it around the Sun 18 times, including 9 planet flybys. The first was an extremely close flyby of Earth on April 10, 2020. Bay Colombo came within just 12,700 kilometers of our planet's surface, about the distance from Copenhagen to Santiago, Chile. Its journey will then take it on 2 flybys of Venus and 6 of Mercury, the last 3 of which are due to happen in September, December, and January of next year. In total, the mighty spacecraft will cover a distance of 8.5 billion kilometers. Taking such a long route was the only way Bay Colombo could slow down enough before approaching Mercury's orbit. But why is slowing down so important? Well, if the spacecraft arrived with too much speed, it would swing right past the planet and get sucked into the Sun's powerful gravitational field instead. Bay Colombo was designed to complement and deepen the findings of its predecessor, the Messenger probe. While Bay Colombo carries many of the same instruments as Messenger did, it is equipped with higher caliber tools able to obtain larger ranges of data. Additionally, Messenger's orbit of Mercury was rather one-sided, as Parapsis was over the South Pole, meaning we have great detail and mapping of the northern hemisphere and almost non-existent data on the southern hemisphere. Bay Colombo plans to rectify this by examining Mercury from an orbital angle more in line with the planet's equator. Bay Colombo is a very unique spacecraft. It's made up of 3 component parts, 2 probes and a propulsion module, which were launched and travel together in a united configuration known as the Mercury Cruise System, run by ESA. The Mercury Planetary Orbiter, or MO, will study the planet's surface and interior, while JAXA's Mercury Magnetosphere Orbiter, affectionately known as MEO, will study the planet's suspiciously low magnetic field that has baffled scientists for decades. The name of MEO was actually chosen by the Japanese general public. It means a waterway, and according to JAXA, it symbolizes the scientific milestones reached so far, and wishes for safe travels to come. MEO and the MO sit either side of an interplanetary propulsion unit called the Messenger Transfer Module. Stacking the different parts of the craft together like this means most but not all of the scientific instruments on board will be inoperative until Biombo settles into its orbit around Mercury. At that point, the MO and MO will be jettisoned from the spacecraft and go their separate ways to study Mercury from different vantage points. But don't worry, there's still enough data being sent back to keep us entertained. Why don't we take a look back at how far this mission has come, what it's already taught us, and explore some of the amazing things it's seen along the way. Music beep. Colombo's first encounter with Mercury came in October 2021. Passing just 200 kilometers above the planet's surface, it sent back some stunning images. As it drifted past, Bay Colombo snapped Mercury's northern hemisphere. To the average person it might look like our rocky, inert moon, but the trained eye sees the Calino crater, which could hold the key to deciphering Mercury's crust composition. The Lamanto crater hosts traces of volcanic activity in mysterious pockets where an unidentified compound in the planet's crust is being lost to space, and scientists have no idea how or why. These images remind us just how enigmatic Mercury is and how much we have left to learn about it. Another camera mounted on the spacecraft caught Mercury from another perspective, one that left the planet's volcanic history on full display. Previously lava flooded and over 250 kilometers wide, the Hayden crater comes into view along with the Pampu facula, one of Mercury's many bright spots, probably formed by volcanic eruptions from billions of years ago. Even though Messenger had already shown us Mercury's volcanic past, it's still pretty amazing that this activity left a mark visible after such an inconceivable amount of time. And Bay Colombo didn't just show us how the flyby looked, it captured how the flyby felt. You know how your phone has an accelerometer in it that helps it know when and how its orientation changes? Scientists mounted a similar accelerometer on Bay Colombo's MO. It measured the movements and vibrations of the spacecraft as it flew past Mercury, creating a sort of sound map of the flyby. Scientists then plotted that data to frequencies US humans can actually hear, so you can actually hear the flyby. I'll play it for you now. Pay attention to the two distinct sounds towards the beginning. They represent the changes in solar radiation pressure when the spacecraft enters and then exits Mercury's shadow. The big clunk towards the end is the sound of the Phoebus instrument assuming its parking position. Here's the clip. Music. Pretty music. Cool, right? I've got another one and it's even better. Pepe Columbumbo captured magnetic field data during its flyby that was also later deciphered and sonified by scientists on the ground. This one is a little more abstract than the other, but we'll give it a go. You're going to hear two synthesizers at the same time. The first synthesizer changes pitch with the changing magnitude of the background magnetic field. A lower pitch means more intensity in the magnetic field. The second synthesizer changes pitch with the variations of the magnetic field magnitude. A more turbulent magnetic field is represented by a faster change in pitch. The dotted vertical line shows where the closest approach was. After the closest approach, you'll hear something that sounds like a DJ scratching a disc. Lots of fast changes in pitch. That right there marks when the spacecraft crosses the magnetosheath where the magnetic field is highly turbulent. Let's have a listen. Music, music, applause. On June 23, 2022, just over halfway in its planned journey, Bay Colombo crossed paths with Mercury once again. This time, the spacecraft turned its gaze towards Mercury's largest impact crater, Calmest Basin. At a whopping 1,550 kilometers wide, it's actually one of the widest known craters in the solar system. Calmest Basin was likely created by the collision of a comet, asteroid, or other celestial object some 3.9 billion years ago. The highly reflective lava craters on its floor make it easy to see as the bright semicircular area of Mercury's disk below the magnetometer boom. The second flyby gave us beautiful images of Mercury's craters like we'd never seen before. Like this one of Hyani, a crater embedded in smooth volcanic plains potentially near an ancient volcano which Bay Colombo plans to examine when it finally settles into orbit. Almost exactly a year later on June 19, 2023, Bayblo reapproached Mercury from a height of just 263 kilometers. The flyby images captured the 600 kilometers long Beagle Rupees, one of the many lobate scarves on Mercury that was first imaged by Messenger in 2008. Other than our moon, Mercury is the only planetary body in our solar system known to exhibit this tectonic signature. When the interior of the planetary body cools, it leads to a global contraction and surface expression of a thrust fault, aka a lobate scarp. Beagle Rupees has an especially pronounced curvature, more so than other scarps on Mercury, offering geologists a rare insight into the planet's tectonic history. As a result of the third Bay Colombo flyby, a large 218 kilometers wide peak ring impact crater received the name Manly after 20th century visual artist Edna Manley. The original basin floor was flooded by lava, giving the crater its visibly smooth interior texture. Bay Colombo will explore Manly crater further from orbit. seeking to measure its carbon composition and detect other minerals that may be present in order to learn more about Mercury's geological history. Gliding past Mercury on its most recent flyby, Baie Colombo snapped a series of farewell Mercury images. At 236 kilometers from the surface, baby Colombo appears to hug the planet goodbye. Scientists back home on Earth will have to wait another 16 months for the next set of images. Now, these flybys are more than an indulgence for our senses. They also revealed important nuances of the planet's particle environment and magnetic boundaries. One of the instruments aboard the MO probe is Phoebus, probing of Hyrian exosphere by ultraviolet spectroscopy. Phoebus uses UV emission from Mercury's exosphere, the planet's outermost and only atmospheric layer, to determine its composition, structure, and interactions with the surface. It does this by detecting specific types of light emissions in the ultraviolet spectrum, ranging from 55 to 350 nanome. By capturing these light emissions across the whole spectrum, it helps us figure out what the exosphere is made of and how its particles are spread out. As Baie Colombo emerged from Mercury shadow, Phoebus detected the presence of hydrogen and calcium, confirming earlier findings from MESSENGER that established the presence of calcium in the planet's exosphere, particularly around the equator and on its night side. Interestingly, this is the opposite of the distribution observed for sodium and potassium, which more readily concentrate around the poles. Once in orbit around Mercury, Phoebus will be able to send back much more detailed analysis of Mercury's exosphere, composition, and dynamics, including how it changes with location and time. Speaking of MESSENGER, back in its day it discovered ice on Mercury's North Pole. Baie Colombo will continue this legacy by continuing the search for ice in permanently shadowed regions of high-latitude craters. As you might know, Mercury is the only planet in our solar system to have a magnetic field similar to Earth's. Thanks to its liquid iron core, Mercury exhibits a dynamo effect which creates an innate magnetic field around the planet. However, Mercury's magnetic field is just 1.1% that of Earth's magnetic field, leaving scientists fascinated with how it's generated. One of the big goals of the Baie Colombo mission is understanding this magnetic field better. So far, the only magnetic activity of the northern hemisphere has been mapped by NASA's MESSENGER mission. Scientists hope that Baie Colombo will be able to shed light on the dynamics of the planet's magnetism in the southern hemisphere. This magnetic field is of great importance. By understanding it, scientists aim to shed light on Mercury's origins, its evolutionary journey, and the current state of the planet's interior. Mo and Mio will travel through different areas of Mercury's magnetosphere on different timescales, simultaneously measuring how the magnetic field changes over time and space, and its relationship to the powerful solar wind. All this new data from the Baie Colombo mission will eventually be compared with global magnetic field models from the MESSENGER mission to build the most accurate picture yet of Mercury's magnetic field, which could unlock telling insights into the planet's elusive past. As we await Baie Colombo's next flyby in September 2024, the journey to understanding Mercury continues. The spacecraft is gearing up for its next major maneuver, a prolonged solar electric propulsion thruster arc planned to begin in early August, and it should last until mid-September. Thruster arcs along with strategic flybys help Epic Colombo break against the enormous gravitational pull of the Sun. This is the only way to successfully insert into orbit around Mercury when the time comes. Once in orbit in December 2025, the real exploration begins. Mercury's heavily cratered surface records a 4.6 billion-year history of asteroid and comet bombardment, which together with unique tectonic and volcanic curiosities, will help scientists unlock the secrets of the planet's place in solar system evolution. Baie Colombo is set to remain in orbit around Mercury for 1 year, and if all goes well, might get the green light for an extra year on the mission. Scientists hope to study the planet like never before. From its composition to its geoisics, its atmosphere and magnetosphere, both its history and the history of other inner planets like it, including Earth. Until then, we've got a few more flybys to look forward to, and the haunting pictures they're bound to capture for us Earthlings back home. Imagine yourself standing on the surface of Mercury, but not the Mercury you usually picture. Not the scorched, sun-blasted daytime inferno. Instead, you're here during the planet's incredibly long night. The sun set weeks ago, and it won't rise for weeks more. Above you, the stars are stark and brilliant against a perfect black, untouched by atmosphere haze. The ground beneath your heavily insulated boots is rigid, radiating away the day's heat into the vacuum of space. It's a silent, desolate landscape. But tonight you've brought special equipment not just for survival, but for observation. You point a sensitive detector tuned to a specific wavelength of light towards the anti-solar point in the sky, the direction directly opposite where the sun lurks below the horizon, and you see it something faint, ethereal, almost unbelievable. Stretching away from the planet, reaching impossibly far into the blackness, is a ghostly, elongated glow. It's a whisper of light invisible to the unaided human eye, a delicate structure millions of kilometers long trailing behind this tiny battered world like the train of a spectral gown. Mercury, the seemingly inert little rock closest to the sun, is doing something deeply strange in the dark. It's venting a tail into space. A tail made not of gas or dust in the way we usually think of comet tails, but of something far more specific and intriguing. Sodium atoms. I'm Alex McCohen and you're watching Astram. Join me today as we delve into one of the solar system's more subtle and surprising phenomena, the vast, invisible sodium tail of Mercury. We'll explore how this bizarre feature was discovered, investigate the complex processes that create and shape it, and understand what this ghostly appendage tells us about the innermost planet and its relationship with the sun. When we think of planets with distinct features, Mercury rarely comes to mind. It's the run of our planetary family, a tiny cratered world baking in the sun. But in 2001, everything changed. Scientists have been using specialized sodium filters to observe Mercury since the mid-1980s when it was found in the planet's exosphere. That's exactly what the team at McDonald Observatory in Texas were doing when they spotted something strange. A faint glow extending far beyond Mercury's tiny disk. Initially they didn't believe their own eyes. They thought it must be the result of an equipment malfunction or data processing errors. But after thoroughly checking and double-checking, the astonishing truth emerged. Mercury was trailing an enormous structure through space, a tail of sodium stretching almost 2.5 million kilometers behind it. For perspective, that's 700 times the width of Mercury itself. The discovery was humbling. Mercury isn't some distant, obscure object, it's one of our closest cosmic neighbors. We've been observing it since ancient times and even visited it in the 1970s and the 2000s thanks to NASA's Mariner 10 and Messenger spacecraft. And yet, this colossal feature remained completely undetected until the 21st century. The discovery was a big deal because it challenged our classification of what can have a tail in our solar system. Suddenly Mercury wasn't just a bland, cratered world but a planet with a dynamic feature rivaling the most spectacular comets. So, how is Mercury's tail different from comet tails, and why would this planet have a sodium tail specifically? The answer is the fascinating result of Mercury's unique position, composition, and the sun's fierce influence. Comets are kind of like snowballs hurtling through space. They are mainly made of ice, which sublimates as the comet approaches the sun, leaving behind a trail of ionized gas and dust particles. In contrast, Mercury is a rocky planet with minimal, if any, ice. Scientists think there may be ice hidden in permanently shadowed craters at its poles, but these frozen deposits remain stable precisely because they never receive direct sunlight. So, Mercury's tail isn't formed through the sublimation of ice into gas, it's made of sodium. But why? To understand that, we need to take a look at its proximity to the sun. At perihelion, Mercury comes as close as 47 million kilometers from the sun, where it's exposed to solar radiation up to 10 times more intense than what we receive on Earth. The solar wind is absolutely torrential. Imagine a constant stream of charged particles flying at 1.66 million km/h from the sun, straight at you. When those particles strike, they physically knock out other atoms on Mercury's surface in a process called sputtering. Picture a bunch of fridge magnets sitting on your fridge. They don't fall on their own because the fridge holds them in place. But then, say you throw a bouncy ball at the fridge, when it hits the energy spreads out and shakes some of the magnets. If enough energy makes it to the weakest magnet, more energy than is what's keeping it stuck, it will pop off and fall down. That's exactly what's happening in a sputtering collision cascade. Ions from the solar wind shower Mercury, creating high-energy impacts that dislodge the weakest link atoms from the surface of the planet, just like the bouncy ball dislodged the weakest fridge magnet. It just so happens one of the most weakly bound elements on Mercury's surface is, you guessed it, sodium. Messenger data show that during periods of high solar wind activity, these solar wind particles rain down on Mercury's surface and result in a 50% rise in sodium group ions in the planet's atmosphere. This indicates that stronger solar wind activity enhances surface particle interactions, leading to a greater release of sodium into Mercury's atmosphere and hail. But there is more to the story. In addition to solar wind, Mercury is also tormented by micrometeoroids, and without an atmosphere to slow them down, even dust-sized particles strike the planet with tremendous force. These tiny space rocks vaporize surface materials on impact, releasing even more sodium atoms. We're essentially watching a process of space erosion, a planet that is slowly disintegrating over billions of years right in our cosmic front yard. Some researchers have noticed enhancements in the tail that seem to correlate with times when Mercury is predicted to pass through denser streams of interplanetary dust like debris from Comet Anchor. This would boost the contribution from micrometeoroid impact vaporization, temporarily increasing the amount of sodium injected into the exosphere and subsequently fed into the tail. But the shaping of the sodium tail isn't primarily due to the solar wind blowing it back, as is largely the case for a comet's ion tail. Instead, the dominant force sculpting Mercury's sodium tail is solar radiation pressure. This is a subtle but powerful effect. Photons, despite having no mass, carry momentum. When a sodium atom in Mercury's exosphere absorbs a photon of light, it gets a tiny push in the direction the photon was traveling away from the sun. It then quickly remits a photon in a random direction, causing negligible recoil on average. However, it's immediately ready to absorb another photon coming from the sun. This continuous process of absorbing solar photons and receiving tiny directed pushes effectively acts like a gentle but constant wind pushing the sodium atoms away from the sun. Imagine countless tiny solar sails, each one a sodium atom being persistently nudged by sunlight. This relentless pressure accelerates the atoms' anti-sunwood, overcoming Mercury's weak gravity and stretching them out into the vast elongated tail structure observed from Earth. Because radiation pressure acts directly away from the sun, the tail reliably points in the anti-solar direction. But as I mentioned, despite being so big, it's not actually visible to the naked eye. So, how did scientists spot it? When sodium atoms absorb energy, they become excited, or their outermost electron jumps to a higher energy level. When this electron falls back to its ground state, it emits photons at a very specific wavelength, 589 nanohm. Light at this wavelength has a distinct color you've definitely seen before. It's the color of old streetlights. This process is happening constantly in Mercury's tail. However, the tail is hidden from the human eye and from standard telescopes. To reveal it, astronomers use specially designed filters called sodium-line filters that isolate light at precisely 589 nanohm. These filters block all other wavelengths, allowing the faint glow of sodium to stand out against the black background of space. By deleting all other wavelengths of light, scientists were able to see the sodium tail. Mercury's sodium tail varies dramatically throughout its 80-day orbit around the Sun, which is highly elliptical. When Mercury reaches perihelion, the increased solar radiation dramatically intensifies the rate of sodium ejection from its surface. You might expect the tail to reach peak visibility at perihelion since that's where the solar wind and radiation are strongest. However, it actually reaches peak 16 days later. Let me explain. Since Mercury's orbit is highly elliptical, its orbital speed also varies a lot from 39 km per s when it's farther from the Sun to 59 km per s when it's closer. Through repeated observations, scientists noticed that Mercury reaches its maximum radial velocity after slingshotting past the Sun, exactly 16 days after perihelion. In other words, that's when it's traveling away from the Sun at its top speed, creating optimal conditions for the sodium tail to extend and become more observable. But why would higher speed lead to a brighter tail? 2 words: Doppler shift. When we look at the spectrum of light from the Sun, we see dark lines called Fraunhofer absorption lines, where certain wavelengths of light are being absorbed by elements in the Sun's atmosphere before the sunlight is emitted. The Sun's atmosphere contains sodium just like Mercury's tail, which absorbs all the sodium-specific light before the light travels to Mercury. But the faster Mercury travels away from the Sun, the more the sunlight is Doppler shifted or stretched. This means the wavelength gets longer, or redder. The entire sunlight spectrum is shifted, including the Fraunhofer lines, so the sodium-specific light is no longer blocked and is available for the tail to absorb and scatter. The result, the tail gets brighter, and we can see it from Earth. So, if astronomers wanted to spot Mercury's tail, they just need to look up on day 16 past perihelion, right? Well, it's not that simple. There are 3 other main factors at play to consider. Firstly, Mercury must be at a sufficient elongation from the Sun in Earth's sky so that it isn't caught in the glare. Secondly, it can't be behind the Sun from Earth's perspective. And finally, it must be at the perfect angle for Earth-based telescopes to view its anti-ward direction. This astronomical alignment only occurs during very specific periods, roughly every few years. And to think the scientists at McDonald Observatory caught it basically by coincidence. Talk about perfect timing. Some of the most spectacular images of Mercury's sodium tail have come from observatories utilizing coronagraphs, instruments that block the sun's direct light, allowing the faint glow of the tail to become visible even when Mercury is relatively close to the sun in our sky. Each successful observation represents a triumph of astronomical planning and precision. These rare glimpses show a dynamic that changes dramatically with Mercury's position relative to the sun, stretching, shortening, brightening, and dimming in a cosmic dance governed by orbital mechanics and atomic physics. But this story stretches beyond Mercury itself. It has provided an unexpected window into key processes occurring throughout our solar system and beyond. Firstly, it gives us a glimpse into planetary evolution. While the current rate of surface material loss is too small to significantly alter Mercury in human timescales over billions of years, this process could potentially affect its surface composition, gradually depleting sodium and other easily liberated elements. We could use this knowledge to infer what might have happened to older planets in other solar systems and understand their life cycle better. Secondly, and perhaps most excitingly, the discovery has profound implications for exoplanet research. Many star systems contain hot Jupiters, massive planets orbiting extremely close to their stars. If Mercury can generate a 2.5 million kilometers tail, these giants likely sport even more dramatic features, potentially shedding significant mass through similar mechanisms. The detection methods developed to study Mercury's tail are now being applied in the search for similar phenomena around distant worlds. By looking for the distinctive spectral signatures of elements being stripped from exoplanets, astronomers may gain new insights into their composition and environment. In fact, we have already detected similar sodium tails around our own moon, suggesting this phenomenon may be common around airless bodies exposed to solar wind. Mercury's sodium tail represents a perfect opportunity for studying planet-star interactions throughout the universe. By better understanding this phenomenon, we gain crucial insights into how stars shape and erode their planetary systems over billions of years. Colombo mission has already completed 6 rapid flybys of Mercury. It's set to enter into orbit in December 2025, where it will spend at least 1 Earthy year studying Mercury's internal composition and its impressive exosphere. This will provide data on the sodium tail in unprecedented detail, promising new discoveries about this fascinating phenomenon. Mercury's elusive tail reminds us that even after centuries of astronomical observation, fundamental discoveries about our closest cosmic neighbors are still being made. What other secrets might our cosmic neighborhood still be hiding? The universe never stops surprising us. All we need to do is keep looking. Music. Everyone knows the name of the first of the planets in our solar system. Mercury was seen in ancient times and carries the name of a Roman god. We've known of his existence for thousands of years. It's not hidden in darkness, but thanks to its position next to the sun is bathed in brilliant light. And yet it is the least explored terrestrial planet, having only been visited by 2 probes in all of our spacefaring history. Why is that? Is it boring? What do we truly know about Mercury? What are its characteristics and history, and how have we learned about it? I'm Alex McCohen and you're watching Astram, and in watching this supercut, you're about to find out. Join with me as I teach you everything you might want to know about the first planet in our solar system, Mercury. When you think about the physical characteristics of Mercury, I'm sure you imagine it being the closest planet to the sun, but also that it's this giant rock floating in space. You wouldn't be too far wrong with that, but it is much more interesting than what you may first think. For example, when I look at Mercury, I do think of our moon. But Mercury actually is visually more appealing than our moon. Look at it in its true color. The first thing that I notice is that it actually does have a color. It's not just different shades of gray. And what else? Well, did you know, for example, that Mercury consists of approximately 70% metallic and 30% silicate materials? So, it's actually more metallic than rocky. Because of this, Mercury's density is the second highest in the solar system at 5.427 g per cm cubed, only slightly less than the planet with the greatest density, that of Earth, at 5.515 g per centimeter cubed. If Mercury happened to be the same size as Earth, that would mean it would pretty much have the same gravitational pull at its surface. But being the size that it is, its surface gravity is only 3.7 m per s squared. If you were to compare its gravity to Earth, it would look something like this. This means the surface gravity of Mercury is only slightly less than what it is on Mars. And considering that Mars is a much bigger planet, that just says something about the density of Mercury. But before we leave the subject of Mercury's size, I want to show you one last comparison. That of Ganymede and Titan against Mercury. Now Ganymede is the solar system's biggest moon and also the biggest moon of Jupiter, while Titan is Saturn's biggest moon and the second biggest moon in the solar system. These two giant moons are bigger than Mercury as you can see here, but their masses are far less. If you look closely at Mercury's surface, you'll see its appearance is similar to that of our moon. It shows extensive Marique plains and heavy cratering, indicating that it has been geologically inactive for billions of years. But it obviously was geologically active at one point because one of the distinctive features of Mercury's surface is the presence of many narrow ridges extending up to several hundred km in length. We'll talk more about these later. One of the most distinctive things you'll notice about Mercury is